f naught k minus L t dt. Now, the expression was like this. And how did we derive it to be sine and cos? Yes, you guessed it right. It is nothing but the Euler's relation, which says if e to the power j theta is given, it can be expanded as cosine of theta plus j sine of theta. Now, let us mark it as, say, x1. We shall have to make two assumptions. By assumption, I mean there are two cases which need to be considered in this regard. That is, case 1, when our value of k equals to value of L, the equation x of 1 becomes, which is x of a equals 0 to, t naught to t naught plus Tp cosine of, now if k and L are equal, this term becomes 0, and consequently all of this becomes 0. So cos of 0 dt. I hope that is understandable. And I'm sorry, the bracket will be here. Similarly, the sine term becomes t naught to t naught plus Tp sine of 0 dt. Quite the similar argument. Now, from our basic trigonometry, this value is equals to 1, and this value will always be 0. Hence, the integral becomes t naught to t naught plus Tp dt plus 0. That is, if this is integrated, we get t, and the range is t naught to t naught plus Tp, which is Tp. Now let us go for case 2, where k is not equal to L, and for that condition the evaluated expression x of a will become 0. Now, how does it become 0 is quite a complicated process. You can do it by yourself, or otherwise you have to take the word that I say. Now, if you look closely, the initial equation that we have started working on has collapsed quite a bit. It has collapsed quite a bit. It was something gibberish like this and this, and it can be now simplified and written as k from minus infinity to infinity c of k summation of t naught plus Tp e to the power of j 2 pi f naught k minus L t dt equals Cl of into Tp or Ck into Tp. Since L and K are equal, we get the value of Tp. Now, a question might be asked, where does the summation sign go? Because if we look back, the summation sign was always there. All we have worked is with this integrand. And to answer that question, Uh, if you look closely, the summation sign is not required. This is because we have considered k equal to L and k is not equal to L. That means only for one value when k equals L, there will be a outcome of t of Tp. Otherwise, for every other value, the value will become 0. So hence, for only one value of the integrand, which becomes Tp, we don't need a running summations. Hence, the equation can be collapsed into CLTP. Now, since L and K are equals, we can write it as CLTP or CKTP. That is up to your preference. And putting this value to the initial equation, to the left hand side, not putting, I should rather say comparing, these are equal. That means T naught of T exp j 2 pi Lt dt was equal to this quantity, which was T naught two pi f naught L of t, not L of t, that is L times t, summation of k, which runs from minus infinity to infinity, c of k e to the power j 2 pi k f naught t dt. We have decomposed this value to be the summation of k, which runs from minus infinity to infinity, t naught to t naught plus tp e to the power j 2 pi f naught k minus L t dt, which we have found to be CLTP. So as you can see, this complicated equation has collapsed into a rather simplified one. And in doing so, we see CL is nothing but the Fourier coefficient, and we can do the cross multiplication to find out the value of CL. That is, so CL will become, if you divide both sides of this equation by T of P, 1 over Tp T naught to T naught plus Tp x of t e to the power minus j 2 pi f naught L t dt. Now, since t naught is an arbitrary value, as I have said before, let us consider the value of t naught to be equal to 0. This does not hamper the equation, and the equation finally becomes sorry once again for the inconvenience. CL now becomes 1 over Tp 0 to Tp x of t e to the power j 2 pi f naught Lt dt, which is the required expression through which we will calculate the Fourier coefficients. Now we can summarize the Fourier series expansion, Fourier series expansion of a continuous periodic as under the synthesis equation, which is nothing but the Fourier series expansion in its exponential form, which is x of t equals summation of k, which runs from minus infinity to infinity, c of k e to the power j 2 pi k f naught t, and the analysis equation which is nothing but the Fourier coefficient that we have calculated, which is c of k 1 over tp, taking an integral from 0 to tp, x of t e to the power j 2 pi k f naught t dt. Now here L and k are interchangeable, as we have seen that the value of this Tp is only achievable when L and k are equal. Now in doing so, we must come to the following assumptions. Number one, which is that the coefficient c of k, as you have seen from this part, is always a complex number. And for a periodic signal, c of k and c of minus k will be complex conjugates if the signal is an even signal. I shall shortly describe the even signal and odd signal. An even signal is nothing but a signal which, when mirrored along the y-axis, will have a same value. For instance, if we draw a cosine curve like this, if we mirror it, we get the mirrored version of this part over here. So this signal is an even signal, whereas the odd signal is that, consider a sine curve. When we mirror the signal, we will get the negative version of the initial signal. As you can see, this part is the original signal, and this part is nothing but the, this one I mean, is nothing but the reverse version of this signal. So this one is an even signal, this one is an odd signal. Other than that, the third assumption is, since Ck is complex, it will always have an argument c of k and a magnitude modulus c of k. Hope up to now everything has been clear. If that is so, let us go to our next topic, which is the Dirichlet condition for Fourier series expansion. Let me write down the conditions first. The first condition says that the signal x of t has a finite number of discontinuities. The second condition is the signal x of t contains finite number of maxima and minimas. The third condition, which says the signal x of t must be absolutely integrable. Now, what does the first point refer? The signal has x of t has a finite number of discontinuities over a period. Let us consider a square wave. Which goes on like this. Now, if you can see, the period of the signal is from here to here, and over this period the number of discontinuities are 1, 2, 3. Why these points are called discontinuities? Because if you consider this point, at the same time the value of t over here is 0, and simultaneously the value can be written as some value, let us suppose to be a. So at this point the value can be 0 or a, or both simultaneously. That's why this point is called a discontinuity. And since the number of discontinuity is countable, so it must be finite. So this signal does fulfill the first criteria of the Dirichlet condition. Now let us go to the second condition, which says the signal x of t contains a finite number of maximas and minimas. Let us consider another signal which goes something like this. Arbitrarily we have drawn a signal where this is t and this is x of t. The signal must have finite number of maxima and minima. So this here is a maxima, this here is a minima. Similarly, this one is a maxima, this one is a minima. Maxima, maxima, here is a minima, and you can understand the rest of the signal. A maxima is a point and the minima is a point where the tangent becomes infinite, if you know what I mean. So since in this signal the number of maximas and minimas are countable, this signal fulfills the Second criteria of Dirichlet condition. Now, if we observe the first condition, that the signal x of t has a finite number of discontinuities over a period. Now, say this is one period of the signal and the signal repeats as before from this point onwards. There are no discontinuities in this signal. So, the first condition is also fulfilled for the Dirichlet condition. It says that the number of discontinuities must be finite number. There can be no discontinuities, which is also under the first condition. Now, applying the second condition to this first signal we have drawn, the number of maxima and minima should be finite. So, this point is a maxima, this point is a maxima, this point is a minima, this point is a maxima, 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 and consequently minima. So, in the pulse train, we can see that the number of maxima over a period is countable. That is, it is finite. So, both the signals follow, or rather I should say, fulfills the first and second Dirichlet condition. Now, the signal must be absolutely integrable. What does this mean? This means over a time period of Tp, x of t dt must always be less than infinity. Now, by this, what do we mean? It means that all of us know from the intermediate concept that the integration is nothing but the area under a curve. So, if we consider this signal over a period, that means from here to here, this area, let me hatch it like this, this area is definable and is not infinite. Similarly, for this signal, the area under this curve, which is this part, negated by this part, this part, this part, and the negative area of this part, is also not infinite. That means the area can be defined to a single value or single expression. That means both the signals follows three of the Dirichlet conditions and can be expanded to the Fourier series. Now, if any signal follows these three conditions, it is guaranteed the signal have a Fourier series expansion. But what happens if the signal does not follow this condition or does not follow all of the conditions? It is not necessary that the signal which does not follow Dirichlet condition will not have a Fourier series expansion. A signal might have a Fourier series expansion if it does not follow any of the Dirichlet condition or partially follows the Dirichlet conditions. Which means that the Dirichlet conditions are sufficient conditions, not necessary conditions. Which essentially means that any signal which does not follow the above condition might also have Fourier series expansion of it. Now, in this regard of Dirichlet condition, we must not worry ourselves, because most of the signal, that is the practical signal we will be working with or we shall face in our future endeavors, always follows the Dirichlet condition. At least most of them follows it. I hope the Dirichlet condition is understandable, and with that, let's move on to the next topic,